And now a little poem about research methods and data analysis courtesy of phdcomics.com. Markings are red, blank screens are blue, professors love data that prove their hypotheses true. A poem which is probably all too telling of some of the recent problems and even crises that we've seen in psychology with respect to the replicability of some of our findings. But anyway, with that in mind, I want to do a little lecture now on redundancy and suppression. These are related topics that have come up recently in some of the lectures that I've done in my class, which is PSYC 440 and 640. It's experimental methods, or more accurately, univariate statistics at NDSU in the spring of 2016. I've talked about them a little bit in class, and I wanted to do a supplemental lecture to give a bit more information and a bit more detail about this interesting topic, or these two interesting related ideas. So today, not much of an overview, just to point out that we're working in the context of multiple regression. That's where we see, or where we can see, issues related to suppression. And it's worth noting really briefly that suppression, the word, conjures some interesting, mostly political images, things like censorship and surveillance. But when we talk about suppression, that is, in the context of applied statistics, it has a slightly different meaning. If you look up in most statistics textbooks or references, suppression, you'll find some phrase or some line like, suppression occurs when a predictor variable has an effect when another predictor variable is held constant. And often you won't find much more information than just that unless you're looking in a good regression-based textbook. I think the reason why suppression often doesn't get as much treatment as maybe it should or as it deserves is because it's kind of a tricky concept to think about. So in order to think about it, let's consider a fairly simple example. Let's imagine that you're a clinical psychologist and you're studying mood. And in the case of this example, you're doing a non-experimental design where you have two predictor variables, some sort of measure of depression, some sort of measure of anxiety, and an outcome variable, which is a measure of low positive affect, or what is sometimes called anhedonia. So if we're going to try and relate those things in a diagram, we might relate them like this. Predictor variables, outcome variables. Let's suppose that depression has a strong relationship to anhedonia. It's strongly correlated, which shouldn't be at all surprising to anyone who's got a background in clinical psychology, because anhedonia, the lack of pleasure, pleasurable activities, is a criterion that's used for diagnosing depression. Let's also imagine that the other predictor variable is anxiety, and that there's a moderate correlation or moderate relationship between anxiety and depression. Again, this is probably something that's not too awfully surprising to anyone who's done any clinical work or has a background in clinical psychology, because these two conditions, or I should say these various conditions, anxiety disorders and mood disorders, tend to be co-occurring. And let's lastly imagine that there's a weak relationship between anxiety and anhedonia. I should note, in this example, this is just data that I've made up, but I've done my best to kind of make it roughly approximate to what you might find if you were doing real research in the real world. Before we go any further, an important idea here is that suppression can occur whenever predictor variables are correlated. And this is more commonly the case in non-experimental designs, where, at least in psychology and the other behavioral sciences, the predictor variables that we're interested in are often correlated with each other. It's somewhat less common in experimental designs, where predictor variables are often uncorrelated. So for instance, if you took equal numbers of people and randomly assigned them to different levels of a predictor variable, like different levels of different groups for different independent or predictor variables, those predictor variables would be uncorrelated with each other. But again, in this example, we're talking about a non-experimental design. We're not assigning people to have different levels of anxiety or depression. We're just allowing that people in our study who we recruit will naturally vary on their levels of anxiety and depression. And we're aware, or at least we should be aware, that anxiety and depression are going to tend to naturally co-vary with each other. So let's imagine we have our data and we want to do a hierarchical linear regression where we enter in the first step the variable depression, predicting anhedonia. We're entering in the first step depression, and then the second step, depression stays in the model and we add anxiety. And let's assume we have a good reason for testing predictors in this order. Maybe we have some hypothesis that anxiety will predict anhedonia above and beyond depression, which is more commonly associated with anhedonia. And this is, again, a contrived example, something I made up, but I was recently reading a textbook or reading a treatment book on anxiety disorders, and there I saw a reference to the idea that high levels of anxiety can make people feel sort of numb to the world around them and make it difficult for them to experience pleasure. So it's not inconceivable that someone might say, look, let's see to what extent anxiety is predictive of anhedonia above and beyond depression, which we already know will be rather predictive of anhedonia. So again, that's our basic idea. And if we were to run an analysis like this in SPSS, we'd get some output that looked a little bit like the following. We have model summaries for our two models, the first containing just depression, the second containing depression and anxiety. And if you focus here on the coefficients for depression, you can see that the coefficient for depression gets bigger in the second model, the second augmented model that is, when anxiety is added in. So this is an example of a suppression effect. You might be wondering, why does this happen? What is it about adding anxiety to the model which makes depression seem to be a stronger predictor of anhedonia? Well, the idea of suppression, can be thought of in different ways, and one way to think of it is kind of conceptually, in this case, that anxiety is somehow suppressing the relationship between depression and anhedonia. Put in slightly more words, we might say that the relationship between depression and anhedonia is stronger, or it's clearer, or it's more obvious to us when the relationship between anxiety and anhedonia is out of the picture. So this could be thought of as an example of statistical control for anxiety using multiple regression. So if we were controlling for anxiety using multiple regression, does the effect of depression or the relationship between depression and anhedonia change? And in this case, apparently it does. Now, just for a moment, consider another interesting possibility. Imagine that instead of using statistical control with multiple regression, we'd instead try to use something like methodological or experimental control. Let's imagine that we'd recruited people who all had the same level of anxiety in our study. So rather than measuring both anxiety and depression and allowing that each of these would tend to vary across some sort of fairly broad range and would indeed co-vary with each other, we instead only recruited people who had, let's say, a very low level of anxiety, or a very moderate level, or a very high level, just some particular fixed level. And in that way, methodologically, or we might say experimentally, we controlled or constrained anxiety, holding it constant. If we did that, we might have observed that the relationship between depression and anhedonia was different than what it would have been if we'd recruited across a broader range of anxiety and depression. So again, had we done this rather constrained, sort of odd approach to data collection, we might have seen a very different relationship between depression and anhedonia among that kind of selected group of folks than we would have seen if we'd recruited more broadly and included people who had very low levels of anxiety and moderate levels and high levels. And it's worth noting that if we'd done that, we also would have necessarily been getting a broader range of depression too, because depression and anxiety are correlated. So again, in this example, we're imagining that anxiety is moderately correlated with depression. That's not difficult to imagine because that's often the case. Now, one way of saying this, or another way of saying this, is that depression is somewhat confounded with anxiety. That means some of what is measured by anxiety, that some of what those numbers on our anxiety scale mean, each participant's score on the anxiety scale that we're using, is really depression. Some of what we're measuring and we're calling anxiety in each person is really depression. The variance in anxiety that's associated with depression is about 14%. You can see here that there's a kind of a modest correlation between the two of them, about 0.4 or so, and we could square that and we would get an r squared to describe the coefficient of determination between those two variables. Yet another way to describe the same situation is to say that these two variables, anxiety and depression, are somewhat redundant. So confounded, redundant, correlated, they're all telling us basically the same thing, that anxiety and depression are not unique and isolated from each other. They are overlapping in some way. So again, depression is somewhat confounded with anxiety. When the model includes just depression, that's like in step 1 of our hierarchical regression, there's some unexplained variance or error. We can think of that as noise that isn't explained by only depression. In step 2, when anxiety enters the model, we could think of anxiety as a confound. That error variance is reduced somewhat. So you can see here, if you look at the residual sums of squares for model 1 and model 2, the residual sums of squares is somewhat smaller in the second case because anxiety is helping us explain some of that heretofore unexplained or error variance. Again, we can think about this as statistical control in the sense that by reducing that unexplained error, or the error that would be unexplained if we didn't include anxiety in the model, we're reducing the noise or allowing for a better signal to detect the effect of depression. The metaphor that we sometimes use here is someone tuning in an old-time FM or AM radio where you had to tune across different frequencies, reducing the noise and sort of honing in on the signal that you wanted to listen to a particular radio channel. Now in this case here, we might describe this as an instance of partial suppression because the regression coefficient for depression gets bigger when anxiety enters the model. So put another way, we could say the relationship between depression and anhedonia gets stronger, or it gets clearer, or it gets more obvious to us when anxiety is in the model. So partial suppression, you might call that. So again, just to return to that important point before, suppression has to do with the relationship between predictor variables, particularly how correlated they are with each other. And so just for the sake of thinking about this a little bit more, let's imagine a situation in which anxiety is uncorrelated with depression. Now, this isn't a very realistic example because it's almost never the case that these things are uncorrelated. But let's just imagine that that was the case. So depression, for the purposes of our imagined example, is not confounded, it's not redundant with anxiety. If we could create some fake data, which I have done, to kind of represent this situation, we'd see something that looks a bit like this. The correlation between depression and anhedonia is basically the same as the partial correlation between depression and anhedonia controlling for anxiety. Just as a quick reminder, partial correlations describe the relationship between two variables, in this case depression and anhedonia, after a relationship with a third variable, anxiety, is removed from both of them. So again, just see here the zero order correlation, the regular unadorned correlation between depression and anhedonia is about 0.62, and that's about the same, about 0.63, that's about the same whether we just consider the zero order correlation or whether we consider the correlation controlling for anxiety, because again, anxiety isn't really correlated with depression in this example. It's also worth noting that the correlation is basically the same as the semipartial or part correlation with anxiety. So if we were considering the relationship between depression and anhedonia after the effect of anxiety or the relationship with anxiety had been removed from anhedonia, we'd see that that part correlation or semi-partial correlation is about the same as the zero-order correlation between depression and anhedonia. And I know it can be a bit confusing, so again, just as a quick reminder, semi-partial correlations describe the relationship between two variables, in this case, depression and anhedonia. After a third relationship, anxiety is removed from just one of them, in this case, anhedonia. So after anhedonia's effect on, after anxiety's effect on anhedonia has been removed, what is the relationship between depression and whatever is left over? And in the case of this imagined example, where depression and anxiety are uncorrelated, it's about the same. So if all these tables are a little bit confusing, or these numbers are a bit confusing, you might imagine this as a Venn diagram instead. So here's anhedonia, here's depression, and in the case of this sort of fake data that I've created, I think if I did my math right, depression overlaps with about 45% of anhedonia. So there's almost half shared variance, which I've tried to represent here in terms of the overlap of these circles. Now, anxiety doesn't overlap with depression at all. It overlaps somewhat with anhedonia. So depression relates to anhedonia, anxiety relates to anhedonia, but in this example, anxiety and depression have no relationship with each other. And thus, removing anxiety's relationship from anhedonia doesn't really change depression's relationship with anhedonia. And to be clear, when we make models that include multiple variables, as we often do if we're doing multiple regression or factorial ANOVA, adding uncorrelated, or what we sometimes call orthogonal predictors, x sub 2, x sub 3, and so on, can improve the overall fit of the model because we're explaining more and more of that outcome variable, y. So you can imagine we're kind of trying to paint over or overlap over more and more of that space in red, y. And that's fine if those predictor variables, x sub 1, x sub 2, and so on, aren't correlated with each other, aren't overlapping with each other. Now, if they are overlapping with each other, we have a situation, potentially, like what we've been talking about in this lecture, of suppression. And with that in mind, let's imagine that anxiety is correlated with depression, which it is both in this example now, this version of the data that I'm going to talk about, and of course in real life. These two mood states, or the formal diagnoses that sometimes go along with them, do tend to be co-occurring. So in this version of the fake data, again, I've tried to create data which is otherwise roughly the same, but in this case, we have depression somewhat correlated or somewhat confounded with or somewhat redundant with anxiety. Here you can see that the correlation of depression and anhedonia is lower than the partial correlation when we control for anxiety. So this is kind of like our classic kind of hint that there could be a sort of a suppression type effect, because if we just look at the zero order correlation between depression and anhedonia, it's about 0.67. And if we look at the partial correlation, where we're controlling for the effect of anxiety on both depression and anhedonia, the correlation is about 0.74. Not a big difference, but a somewhat big difference. Also, if we go and look at the semi-partial or part correlation with anxiety, you can see again that it's the zero order correlation is somewhat lower than the semi-partial or part correlation. Again, just a reminder here that the semi-partial correlation is describing this relationship between the variables after a third variable, anxiety, is removed from anhedonia. Now, if we want to imagine what this looks like in terms of Venn diagrams, we could say this is anhedonia, and depression overlaps with anhedonia about 45%, and depression overlaps with anxiety about 14%. My scale is probably not that great here, but the point I want to show, or at least try and illustrate, is that whereas before there was no overlap between anxiety and depression, now, in our somewhat more realistic version of the data, we're allowing the anxiety and depression overlap. Each of them overlaps with anhedonia, but both of them overlap with each other as well. Now, if this is the case, then removing anxiety's relationship with anhedonia increases the relative overlap between depression and anhedonia. Now, this is one of those things you either probably see or you don't see. I think for some people Venn diagrams can be really useful. For others they can be a little bit confusing. But the way to visualize this is we've tried to sort of take out the piece that anxiety has overlapping with anhedonia, and once we do that, we have a relatively large amount, relatively speaking, that depression can overlap with anhedonia. So again, in these examples here, or this one previous example, we allowed that our predictors were somewhat correlated or somewhat confounded or somewhat redundant with each other. This gave us a situation of partial suppression where the regression coefficient for one of those predictors, depression, got a lot bigger when the other predictor variable, anxiety, entered the model. You might be thinking to yourself, what about a situation in which our two predictor variables were rather highly correlated or confounded or redundant? Well, I tried to create a situation like that, kind of keeping the overall configuration of the data the same, but instead allowing that there would be a strong relationship between anxiety and depression, a stronger correlation. Again, the overall correlation between depression and anhedonia is about the same as it was before, and the overall correlation between anxiety and anhedonia is about the same as what it was before, as best as I could figure just fiddling around with the data. The change now is that depression and anxiety are more strongly correlated with each other. If we did this and then ran a hierarchical regression in the same fashion as we did before, now the output from our analyses would probably give us the impression that depression is rather confounded or rather redundant with anxiety. So if we look at the simple correlation between the two of them, we see that about half of the variance in anxiety is associated with depression. In the previous example I gave, or the previous example of partial regression that I gave, the overlap was about 14%, so it's quite a bit larger in this case. And another way to put this is that these variables are now quite redundant with each other. So depression is confounded with anxiety just as before. When we enter the anxiety into the model, we see a fairly big reduction in the error that needs to be explained. There's less, or not error that needs to be explained, but there's less residual error, less error variance that is unaccounted for in our model. We also see a situation in which the regression coefficient for depression gets quite a bit larger when anxiety is added into the model. And we might also be tempted to say that if we look at the overall model summary, that the model only, quote, gets significant, unquote, when anxiety is in the model. So this is kind of giving us evidence of what we might call full suppression. Your depression just doesn't really seem to do much on its own, but then you add anxiety in and bang, oh, depression does a lot. Some people would call this full suppression. It's interesting to note that suppression is quite confounded with anxiety. If we look at the zero order correlation, it's quite a bit lower than the semipartial or part correlation between depression and anhedonia, controlling for anxiety. So sort of further kind of evidence of a kind of a suppression effect. It's also worth noting that as the correlation, or we might call it the collinearity, between our predictor variables increases, the tolerance for of any one of them for the others goes down, and the variance inflation factor goes up. So you can see that tolerance starts to drop below 1 when anxiety is added to the model, and variance inflation factor, which is just the inverse of tolerance, goes up. So shifts in tolerance, shifts in variance inflation factor signal problems with multiple collinearity, and also make us think that we might be dealing with a situation that has to do with suppression. So if all of this is still a bit much for you, here are a few important points to consider as we wrap up. One, although I've talked about partial suppression and full suppression, and although you sometimes encounter these terms in textbooks or in references, there really isn't a precise line, at least not that I've seen, between what is full suppression and what is only partial partial suppression. It really just has to do with how correlated the predictor variables are. And that's something you should be thinking about anyway when you do multiple regression, or you do factorial ANOVA, or really any sort of situation where we have multiple predictor variables. The more highly correlated predictors are, the more problematic they are for models, because they create situations in which the predictor variables share variance with each other, or put another way, the situations in which the variables are each individually measuring kind of something that the other is measuring, or they're measuring kind of the same thing. So although we may think of anxiety and depression as being distinct, and although we may have separate questionnaires for them and separate columns in our data set, really they're kind of the same thing, or at least they're somewhat the same thing, depending on how highly correlated they are. And to the extent that predictors are highly correlated, it becomes difficult to interpret their individual contribution to the overall model. In the case of our full suppression example, it kind of looked like depression really doesn't do anything by itself until anxiety enters the model, and you might be you might be tempted to conclude that depression has little relationship with anhedonia, which probably from a theoretical perspective wouldn't make a lot of sense to you. It's kind of an artifact of the way those variables are measured and how they're entered into the model. So again, it's important to think clearly about your predictor variables and try to understand a little bit about their relationships with each other before jamming them into a multiple regression or a factorial ANOVA or some sort of analysis like that. A couple more tips for checking for suppression. Basically, look for situations in which variables, predictor variables, are highly correlated with each other. Here are some rules of thumb that come from the Cohen-Westanaken textbook, which is a reference that many of us are familiar with. If you have a situation in which the predictor variables are more strongly correlated with each other than either is with the outcome variable, you may very well end up with suppression. So you might, for instance, take the correlation between the first predictor variable and the outcome and see if it's smaller than the product of the correlation between the second predictor variable and the outcome and the two predictor variables, or vice versa. That's just kind of like a quick check that you could use to see if you might have a situation where there's suppression. Another situation in which suppression could come up is where the correlations between the predictor variable and the outcome, or a correlation between predictor variables is negative and the correlation between either the predictor variables and the outcome is positive. So if you had two predictors which are, say, both positively related to an outcome variable, but those two predictors are negatively related to each other, that could lead to a suppression situation. So in the textbook, Cohen-Westanaken give the example of working in a sort of industrial organizational setting in which social skill is predictive of job performance. People who are more friendly and socially skillful tend to do better or get better ratings of their work. Let's imagine that that correlation is about 0.4. Record keeping, how diligent you are at filling out forms and checking off boxes, maybe that's also related to job performance. But let's imagine that social skills and record keeping are negatively correlated or negatively related to each other. This could be a classic situation for suppression, where the effect of one of these predictor variables would only show up or would be strengthened when the other predictor variable was entered into the model. Another example that Cohen-Westanaken uses from kind of economics, where cutting taxes is related to economic growth. That's sort of the mantra of many conservative politicians. Inflation is also related to cutting taxes. So if you cut taxes, people have more money, inflation increases, and maybe inflation is negatively related to economic growth. It devalues currency, it makes savings less valuable, and so to the extent that inflation goes up, economic growth slows down. Another example of potentially a suppression effect where one of those predictors, inflation or tax cuts, would be related or would be more strongly related to economic growth only when the other was held constant. So two kind of examples there of this, of just further examples of suppression. So anyway, this has all been a fair bit of complication to talk about. I hope you've stuck with me and not gotten too confused. If you are confused or if you have questions, ask me, please. in the meantime, like I always say, thanks for your attention. Fix yourself a cup of tea or a cup of coffee and let this all sink in for a few minutes. Hopefully it'll make sense to you. And once again, if you have questions, do ask. Thanks so much. Bye-bye.